So I want to do two slightly different things in these two halves of this lecture. I want to continue playing games with intersection numbers, with divisors and intersection numbers. So, you know, the general thing is here, there's a linear system, D, and maybe we want it to be free. In other words, no base locus. And so, you know, there are different games you can play there. I'm going to sort of remind you where we are in this Bombieri program, and this trying to prove these ampleness systems. And then I want to go on to talk a little bit about, you know, more singular curves and their dualizing sheaf. So I want to think about omega d, and the d may be non-reduced. Right. So we get to a point where sort of saying, well, it's omega 1d, you know, just doesn't work. And so we have to understand what this duality is. So this is Grothendieck-Serre duality. Right. So eventually, I will use this in the next lecture next week. I'll use this to re-attack, to give a slightly different attack on this problem of free linear systems. Right. And so you know, eventually we're going to be working with curves, which are curves on surfaces, but which are basically arbitrarily singular, or mostly arbitrarily singular, and not certainly non-reduced. Okay, so let me just remind you of where I've got to. I have you know, curves you know, on a non-singular surface, non-singular projective surface S. And so we have intersection pairing. And we have this index theorem that I've described. So the index theorem very often allows us to say some inequalities on what these intersection pairings are. Typically, you know, my favorite one is this a squared ab b squared less than or equal to 0. If, you know, and I'm not saying the conditions again, under some conditions. Right. So this is just a very useful thing to be able to say about curves on the surface. Right. And so I had these results about numerically connected. So you'll remember the definition is D is an effective divisor. It's numerically K connected. Means that whenever I can write D as A plus B with AB positive, then effective divisors, then A times B is greater than or equal to K. Right? So the thing we're trying to avoid is something like this, A, B, and only one point. So if this happens, this point will certainly be a base point when I take canonical class plus this divisor, and this is what I'm trying to avoid. So avoid this thing here. So that if I have this, then there's one point there which is a kind of weakness of the curve, and I'm trying to avoid that. So this definition does this. Okay, and just to remind you of this thing which, well, I sketched all the proof, but maybe I didn't state it. Example, if K is nef and big, right, this is for a surface, a surface of general type, then D in RK is two connected, numerically two connected, except, so I didn't really state this. I mean, I proved it, but I didn't really state it, except R equals 1 and K squared less than or equal to 2, or R equals 2 and K squared equals 1. Right, so I mean, this case really happens. You know, if K squared is 1, then I can have A and B, both A twiddles B, numerically equivalent to B, numerically equivalent to K, and then it can happen that 2K, this is 2K, is this A plus B, and then it's only K squared is 1, so I get this. But in any case, these are very, very, very small examples, right? So D2 connected implies that K plus D is free. Or so if P is in singular of D, then K plus D is, okay, I'm not saying it. D is 2 connected, P in a singular point of D. This implies that P is not in the base locus of K plus D. Right, so in this case we proved this this thing for, in this case, for K plus D. Right, and you know, exactly the same argument would say that D is 3 connected, P and Q are both in singular of D, implies that the linear system K plus D separates, I'm going to explain this in just a while, separates P and Q. Right, so in other words, the map defined by this linear system K plus D certainly separates this thing. However, but minus 2 curves usually contradict 3 connected. Right, so this is not, as it stands, this is not quite the right way to deal with it. So, you know, if I just run exactly the same arguments I used to prove this, then I will find that D is 3 connected, except for a small number of silly initial cases, and except for the possibility that there are minus 2 curves. Okay, so this is not the right way to go. Or it's not it's not the way that I intend to go. But Bombieri did this properly. Okay, so I want this criterion for very ample. So I'm sure that a lot of you know this from reading Hartshorne, but let me say it again. So I've got, if X is a scheme, so let's say a projective scheme, and H a line bundle, a Katia divisor, and I look at H naught OX of H and I use this to define, I choose a basis here, x0, x1, up to xn, and I try to use this linear system to define a map phi h, I mean it depends on the basis as well, but let me just assume this, maps x to p n. Right, this is given by p maps to xi of p. Right, and so I want to give a criterion for this to be, so everybody knows, we know that x maps to phi to x in Pn is an isomorphism or isomorphic embedding or an, okay, so that's this criterion for very ample. If and only if, so I want, let me state it as three conditions, although it's really just two conditions. The third is you can write 2 and 3 together. So for all p in x, one of the x's, one of the xi is not in h0 of mp times O x of h. Right. So here's here's my point on the variety. So this Ox of h is locally free. Right. On the other hand, I've got this section. I want to find this section xi in Ox of h. Right. And this condition here says that xi is a local basis. Right. So if I take a local basis, then I can write xi equals some function times the local basis. That's what it means to have a local basis. Then I'm saying here that this xi is a unit multiple of a local basis, so it's itself a local basis. Right. And the second condition is that for all p and q, I can find xi. I can find two of these guys, xi, xj. That's base. I'm sorry. Let me say it like this. I can find two linear combinations of the xi, so that xi at p is not equal to 0. Xi at q is equal to 0. So sorry, this is two linear combinations. So I'm going to write xi 1 and xi 2. So that xi 1. So this one's not 0 and this one's 0, and the other way around. Xi 2 at p is equal to 0. Xi 2 at q is not equal to 0, is equal to 1. It's not equal to 0. Right? So this just means that if I take Ox of h, and then I go into here, Ox of h times mp1 times mp2, right, this goes on to kp1 plus kp2. Right, then I want this map here to be, when I do h0 here, I want this to be surjective. Right, so these two guys here, x1, xi1 and xi2 map to a basis. They map to 1, 0, and 0, 1. Right, and so this condition is just saying that the map here takes two different points of x to two different points of the image. Right, and then the next condition is this third condition is called separates. So this condition is called separates points. Right? And this condition says separates tangent directions. Right. And so this, the way I'm going to say it is this. I take MP in OX, and let's take some J inside MP, so that this is colength 1. Right, so if you want, this corresponds to J, corresponds to a codimension 1 subspace of MP mod MP squared. Right, so this is the cotangent space. This is the tangent space to P at X. Dual, the cotangent space to X. Right, and so I'm saying if I've got a vector in the tangent space, then this J here is the set of elements of MP squared. Sorry, the elements of MP that vanish on this vector. Right. Then I want that H naught of I want that these xi's, some linear combination of the xi's of the x of these guys xi's. I want first that there exists an x1 at P is not 0, and then that there exists an x2 at P, which is equal to 0, but x2 is not in J times OX of P. Right, and so this is just the same thing here. I have J times OXH, and then it's mapping onto the kernel, the co-kernel. Right, so the co-kernel looks like this co-kernel here looks like K of T divided by T squared equals 0. Right, so it's still a two-dimensional vector space exactly as here, but here it looks like a point and a tangent vector at a point. Right, so this is called separate tangent direction. Okay, so this is there's a sort of proof of this which says first x maps to, let me write phi of x. Let me call this y. This is 1 to 1, and then I have to prove that this is the map phi. This is in Pn, and then I have to prove somehow or other that when I do OY here, there's OY, and that's there's also automatically contained in phi lower star OX. And I have to prove that these two things are the same ring. And the way you do it, so I'm going to take my here, and I'm going to take phi lower star of m. So the same point x. This is inside here. That's mx. And I have to, I prove that these are equal using this together with Nakayama's lemma, together with the fact that this phi lower star OY OX is still a coherent sheaf on y. So there are two or three things to say here, and let me just cut it a bit short. This proof is in exactly these words in Hartshorne. Right. So you remember that when we were doing curves, for curves, especially the canonical class of C, right? Then I say that Kc minus P, H naught of Kc minus P, is contained and not equal to H naught of Kc. So if C is genus greater than or equal to 1, this is for all P. Right, and if C is of genus greater than 2, then also H naught of Kc minus P minus Q is, so there are two cases here. This could be equal to H naught of Kc minus 1, this is the genus minus 1, or it could be equal to H naught of Kc minus 2. Okay, so in this case, so this is the normal, this is the usual case. This is the case that I take all the sections in Kc, I'm using it to give a map of my curves, I take the 2 points P and Q, and they impose linearly independent conditions on the sections of here, and that means that the 2 points are mapped to separate points of space. Right, so that's the normal thing, the thing that usually happens. Right, then there's this exceptional thing. So this, the first exceptional case is that all the sections vanishing at P also vanish at Q. And this means that Kc minus P minus Q is bigger than expected, so this is irregular linear system. Right, and this implies by Riemann-Roch that also P plus Q is irregular. So you do the numbers and you find out that P plus Q is a G12. And this means that C is hyperelliptic. Okay, so I mean, I'm saying this is just to reassure ourselves that we're going in some sensible direction. When we do the canonical class of a curve, then you know, for a linear system on a curve to be base point free or to be very ample is this very simple condition. I just want to calculate these numbers and assure myself that these numbers drop by 2 when they should. Right, and so you know this theorem here is very you know, it's the first theorem you prove after you prove Riemann-Roch. So this gives you know, genus 3 curves are C4 in P2 or double cover of P1 with 8 branch points. And G equals 4 is C equals quadric intersect cubic in P3, or a double hyperelliptic double cover of P1 with 10 branch points. Okay, and you know, and so this, in other words, here I start off from an abstractly given curve of genus 3. And this is abstract, and then it maps to C4 in P3, C4 in P2, etc., the other possibility. And this is a concrete model. This is a model of the curve embedded in a space and given there by an equation that we understand. Of course, when the genus gets bigger, the situation gets more complicated, but the theorem still holds. Right, and so what about surfaces? Well, you know, it's much harder. So it's much harder technically because a linear system, you know, a finite dimensional space of functions on a surface is a linear system, and then the linear system consists of these curves, and the curves have geometry in their own right. Right? And it's also more complicated for other reasons. You know, we're going to, so the typical case of surface of general type is a bit more complicated, and I'm going to explain what this is. Right. So what else do I need to do here? So I'm going to leave this. So I want to talk about you know, so Bombieri's results. So this will be next lecture. Say you know, give, you know, 3K or etc. Ample, very ample on the canonical model. Right, and so and so there are, you know, and also we understand about 2K. So you know, as I said, there are some exceptions here. I'm not trying to make a correct statement. Right, so we don't get anything directly for the canonical class, and you know, there are reasons for that, because the theory of surfaces really is much more complicated than the theory of curves. Nobody knows already in fairly simple invariants. Nobody knows all the surfaces of general type. Okay, so anyway, this is for next time. Here I want to talk about something called the Horikawa analysis, or at least the beginning. So what happens, this is what happens when PG is comparatively large and K squared is small. So what we're now we're going to so especially I want to say PG is greater than or equal to 3, then K squared is greater than or equal to 2PG minus 4. This is a theorem. And for K squared close to this bound, we get good control of surfaces. Using the canonical map. Phi k. Right, but close to this bound means either equal to the bound or equal to the bound plus 1 or equal to the bound plus 2. If you go much higher, you immediately get into big problems. So I'm going to talk especially about PG equals 3, K squared equals 2, K squared equals 3. These are okay, and then K squared equals 4 is already much harder. And PG equals 3, PG equals 4, K squared equals 4. That's the smallest bound. 5, 6 is harder. And 7 is, you know, not really settled. There's a book of Ingrid Bauer on this subject, which you know, I mean, has a lot of detailed results and so on, but not really not really a convincing conclusion. So you know, this is a sort of Horikawa was working. This is, you know, around 1975 to 1985. Well, let's say something like this. And you know, for me, and for people immediately in the next generation, we learnt a lot from this. So. Okay, so let me explain the idea here. So I'm going to assume that S is a minimal non-singular surface of general type. Right, and this means essentially by definition is Ks is Nef and K squared. K squared is Nef and B. Right, and I'm going to look at this linear system Ks. Right, so it has dimension Pg minus 1. So it's I'm thinking of this as being a family of curves moving around in a linearly parametrized family on the surface. So the first thing that can happen, it could have base curves. Right, so there's this vector space H0 of Ks. So this is x1 up to x Pg. Pg is just a dimension now. And so I can ask the base locus is the scheme, is the, well, it's really the ideal I in OS, such that H0 of Ks maps to H0 of IS, I times OS, OS of Kx. Right. So I'm hoping, if I'm hoping that the linear system is free, then that means I'm hoping that one of these xi's here is a basis, is a local basis of this locally free sheaf at every point. Right? And so I can, for every point P, I can ask, does he map to a basis? And, well, he maps into some ideal here. I is just the, or if you like, I is the image of OS tensor H0 of Ks. Or it's the I times OS of Ks. Right? And so this I here is some ideal, and he could vanish on curves or on points. Right? And then so how am I going to say this? I'm going to say, suppose that Ks is a free linear system, a fixed part plus a mobile linear system. This is the first thing we do, F plus M. So this is the fixed part. So in other words, I'm thinking that here, this I here, this I is the ideal of the base locus. I'm just asking for the biggest sheaf of ideals, OS of minus D, contained in I. Right, so I'm asking, I take all the sections, all the elements in this I, and I ask what's the biggest curve they all vanish on. Right, so this is F. Right, this is, so here's my S. Here's some of these curves D in Ks. right? So these are moving around, right? Except some of them may be fixed, right? This means that there's some curves here that don't move around, right? And then it can also happen that so M, this is mobile part. So now this is moving. This moves around without fixed components. So, so what's the idea? What do I want to say here? So, first of all, I want to say that k squared is equal to kf plus km. So, you know, I'm hoping this f is 0, but at least the f is an effective divisor, and k is nef, and so this guy here is greater than or equal to 0. Right, so this is greater than or equal to km. Right, and I'm going to play the same game with m. So km is f plus m times m, and so this f times m here, this is greater than or equal to 0 because m is mobile. Right, so you know, whatever the components of f are, the m doesn't have any fixed components, so I can move the m so as to avoid containing any component of f. So this guy here is greater than or equal to m squared. Right, and then what can we say about m squared? So now m is a mobile linear system on S. And so it's defining a map phi m. It's now defining a map S maps to some image of f in P. So the image is just that I mentioned this vector space, PG minus 1. Okay, and now there's going to be a division of cases if phi m of S is a curve. Right, so let me say straight away, this Ks is a sub-variety of P, PG minus 1, and whatever else it does, it certainly spans P, PG minus 1. Right, so it's not contained in any hyperplane. So why is that? Because if I take O of 1 here, I take sections H naught of O of 1 here, and I pull these back. I do phi up a star of these guys. Phi up a star of these H naught of O1. Right, then this maps to H naught of Ks, and it maps isomorphically. Right. So if the image were contained in some hyperplane here, for example, then this image of this hyperplane would be identically 0 on S, and that just contradicts this. Right. So this is non-degenerate. It's the image is some variety in there. So if the image is a curve, then the general element of M is has at least PG Pg minus 1 irreducible components. Okay, so yeah, maybe I should say. So in this case, what I've got is here is the image curve. Here is the surface S. Then, you know, possibly after ignoring or blowing up a few points of S, whatever the remaining base points of S are, then each point of the curve pulls back to pulls back to a component of M. Right. So the point is just that the image here, the image is a curve. So when I take a hyperplane section here, I'm cutting the curve because it's a curve that spans Pg minus 1. It has degree at least Pg minus 1. Right? That means that when I cut it, I have at least Pg minus 1 points. But I take those curves, I take that element in here, and it's really a section of H naught of Ks. The place where the H naught of Ks vanish is a union of curves, and each one of these curves has to map separately to each one of these points. So in this case, we say that Ks is composed with a pencil. So we know this is an old subject. It goes back to the 19th century, and there's these strange terminology in it, right? But the thing that's happening here is that the image. One possibility is that the image is not a surface. I'm hoping this image is I'm really hoping that this is very ample. So if it's a curve, we're quite unlucky, and then we use this funny expression composed with a pencil. Right. And so, you know, lemma, this is just basically trivial. Lemma, in this case, remember I'm assuming here that PG is comparatively large. So let me assume that PG is greater than or equal to 3. In this case, K squared is greater than or equal to 2 PG minus 2. Right? So the only thing I'm saying here is that here is my M, and the M contains a subsystem consisting of reducible curves with at least greater than or equal to PG minus 1 components. Okay, so the point is this M here contains all these curves. So the M itself, every element in M looks something like this, containing at least PG minus 1 curves. Right. So that when I do Ks times M, right, this is greater than or equal to Ks times each of these curves, and in practice this is greater than 2 PG minus 2. Right. So you might say, well, what happens? It's possible also that K times each of these curves is equal to, it could be, well, K times each of these curves can't be 0 because K is big. Right? If K times each of those curves is 1, then each of these curves itself has to have intersection number greater, odd intersection number, and therefore intersection greater than 1, greater than or equal to 1. In that case, I'm going to get PG minus 1 all squared, which is always bigger than this. Okay? Sorry, I'm saying this a bit quickly, but it's basically elementary, right? So if Ks times gamma I, let me say gamma I. If Ks times gamma I is greater than or equal to 2, then we get this, right? But if Ks times gamma I is equal to 1, then gamma I squared is greater than or equal to 1, just because it's odd. Remember, Ks times gamma I and gamma I squared are congruent modulo 2. right? And so then I'm going to get this PG minus 1 all squared. And in all, for PG greater than or equal to 3, that's greater than this. Right? I mean, this case, this second case basically only happens in one or two very, very trivial initial cases. Okay? So I'm thinking of I'm trying to prove this Horikawa inequality, where it is k squared is greater than 2pg minus 4, and in this case I'll prove something slightly better. So the next case is phi k from this is phi m from S to phi m of S in PG minus 1. So we can assume that the image is a surface. Right, and so let's assume that phi m is not birational. So this means it has degree greater than or equal to 2. Right, then m squared is greater than or equal to 2pg. Sorry, m squared is greater than or equal to. Sorry, m squared is equal to the degree of the base locus, the zero-dimensional base locus of M. So here are my curves in M. It could happen that they all pass through a point. We'll see examples where this really happens. So there's a zero-dimensional base locus, and if that is there, then it contributes. It will make some difference here. And then plus the degree of phi of M times the degree of the image. Right? And we've agreed that this one is greater than or equal to 2, and this one is necessarily greater than or equal to PG minus 2. Okay, so why is this? Because the image is a surface, so this is a lemma. I mean, it's basically obvious. An irreducible surface S in Pn has degree greater than or equal to n or n minus 1.
You mean number generator?
Yes, spanning. Okay, so I mean, this is. So if I take that surface and I cut it by a hyperplane, I get a curve that still spans its Pn minus 1. If I cut it by a second hyperplane, I get a finite set of points that still spans Pn minus 2. A linear section. S intersect H1 intersect H2 is a finite set of points, and it spans Pn minus 2. Okay, so this is straightforward. So in any case, maybe we lose a bit, maybe we gain a bit here, and we gain a bit here, and maybe we also gain a bit here. But so the point of the Horikawa analysis is to understand that this puts very, very strong restrictions on the geometry of n. And anyway, we get here greater than or equal to 2pg minus 4. Right, so 2pg minus 4 implies that this is 0 and that the other terms in there are 0. Right, and so the birational, so the last case, the final case of this proof says, which actually I haven't prepared, so if phi m is birational, then the image is a surface. So S, so you know, I don't know. S prime in P, PG minus 1. And it has which is not rational or ruled. Right. So I'm not going to explain this. I haven't prepared this proof, and but it's well, the thing I'm saying is easy. Then Clifford's theorem on curves. Implies that degree of S prime is greater than or equal to the degree of a K3 surface in the same space. So that's 2 PG. PG minus 3, I think. Anyway, we'll see better results later. You know, in fact, we're going to get greater than 3 PG minus 7, but I just haven't. I can't remember how you prove it. Let me just leave this. So the conclusion of this argument is that the conclusion, which I stated earlier, if PG is greater than or equal to 3, then K squared is greater than or equal to 2PG minus 4. Right, so it's proved separately in these three cases. There's a case where it is composed with a pencil. There's a case where the map is generically finite, but not an isomorphism, not birational, and then there's the birational case. But let me explain this interesting geometry in these, especially in these cases. So let me explain these cases. So this is the beginning of the theory of surfaces, the classification of surfaces of general type. So PG equals 3, K squared equals 2. So what's happening? We follow the same these arguments give. So I have this K squared is greater than or equal to m squared greater than or equal to, and then here I have the degree of the image, the degree of P2 times the degree of the map. Right, this number is only 2. Right, this number here is 1, so that's not especially scary. The degree of the map. Well, as I said, in the case where the thing is composed with a pencil, I get slightly more. So this degree of the map is greater than or equal to 1, On the other hand, if the map is of degree 1, it means that the surface is mapped birationally to P2. Right? And that's a contradiction. So actually this is 2. And so the thing that happened here is, you know, I allowed for the possibility that there's a fixed part. I did various numbers on it and so on, and it turns out that you get. And then I allowed for the possibility that the mobile part of the linear system has still has a base locus. But in any of these, you know, because I have 2 here, and I have only 2 there, then in fact the linear system is free. So in the above analysis, if k times f equals f times m equals 0, implies that f is actually equal to 0. Right, so this is again by the index theorem. Right, and so therefore the conclusion in this case is that if Pg equals 3, k squared equals 2, then phi k from S to P2 is a 2-to-1 covering. So phi k, ks is free, and it's a 2-to-1 covering. Right, and so, you know, if you study this just a little bit more, you'll find out that, that S over P2 is a double cover ramified in a curve of degree 8. Right, and you know, the way that we tend to write this nowadays is we think of this as being S of degree 8 in the weighted projective space. I'm going to have quite a lot more to say about this later. 1, 1, 1, 4. Right, so you know, how I calculate the degree of this branch covering I can explain later, but you know, I have canonical class of S is 1/2 of canonical class of P2 plus the branch locus. Right, and this is basically O of 1, and so this is -3, and then this has to be plus. I'm sorry, this is 1/2 of. I'm sorry. This one's -3, and so this one has to be 8. Anyway, let me not worry about this too much. The conclusion. Let me just explain what the conclusion means. So it means I've got x1, x2, x3. This is just the basis of h0 of ks. Right. So this defines this map, 2-to-1 map from the S8 to the surface here. Right, to the to P2. Right, and then on top of that I have this element Z in degree 4, and Z satisfies an equation Z squared equals F8 of x1, x2, x3. Right, I've completed the square here. I've in order that I'm not seeing a linear term in Z here, I've completed the square. Right, this can be a nice non-singular surface. The term Z is here, which means that the surface doesn't pass through this cone point at all, and this is defining a nice non-singular variety. And so you know what we've done, what this argument does here, is, you know, the ideal case. This is the best possible model for a surface. Namely, I start off with an abstract specification of the surface. I want surfaces satisfying this abstractly given surfaces, which are surfaces of general type satisfying that condition. And I get a model here, which is uniquely specified. There's no ambiguity in this. And it's just a hypersurface. So I get not just a single example of a surface like this, I get all of the moduli of the surfaces. So this is every surface with these invariants. Is given in this way, is given as S4, S8 in P1114, and also the parameters that S depends on is a vector space of F8. Right, so in this case we get not just a single surface, we get also the moduli space of these surfaces. So this is, you know, this is a rare, beautiful example. Because there are two different models. Sorry, PG equals 3. Two different models. So family 1, Ks is free, and phi Ks from S to P2 is 3 to 1. Okay, now we don't know, I can't just write down the equation of a cubic model, but it so happens that then, so it happens by graded ring methods I'm going to talk about later in the course, that S is then equal to, the canonical model of S is S6 in weighted projective space 1, 1, 1, 2. Right? So in this case I write down x1, x2, x1, x2, x3 and y, and then I write down an equation y cubed plus a 4y plus b6. And these a4 is a4 of x1, x2, x3. b6 is b6. Right? And you know, this is, I mean, this model here is very beautiful, and if you see this model, then you say, well, you know, what else could happen? Well, what else could happen is exactly what's specified here. There is another possibility. So there's a second family. It can also happen that Ks has a base point right? So what it means is here, you know, I've got three functions, the equations of the three curves. So, you know, there are three of them, so I could avoid every point on the surface if I was lucky. But it so happens in this case that we're unlucky and that these three come together in a single point. Right? And then phi Ks from S to P2 blows up the base point and is 3 to 1. and it's 2 to 1. So in this case, S is the canonical image of S. This means, I should really write X to this thing. If S has got any minus 2 curves, I've contracted them to points. This S is S. So there's still a 6 there, but it's S3, 6 in weighted projective space 1, 1, 1, 2, 3. Right. So what's happening here is I'm writing down x1, x2, x3, y, and I'm putting in this element z here. And I've got an equation here in degree 3, and I've got a new generator in degree 3, and I've got a new relation in degree 3. So the relation in degree 3 doesn't involve z. Right. So I'll let me leave this for the moment and come back to it next week, because it's very pretty example. So what I'm doing here is I'm writing down 2 equations which I can think of as being, for example, x1 times y equals quadratic in x1, x2, x3, and then another equation which is saying, for example, z squared plus y cubed plus other terms, ay, a4y plus b6 equals 0. Right, so I've got now 2 equations. So, this looks sort of surprising, but, if I tell you I'm going to write down these equations here, and I want these to define a non-singular complete intersection surface in this space, well, I'm putting in the z squared and the y cubed here, so this hypersurface just doesn't see these 2 singular points of the weighted projective space. And then, you can easily calculate the discriminants. Well, you can calculate the discriminants of these equations, and you find that it's non-singular. So, there's a moral here, which is I was talking about these restrictions on how much fixed part the linear system can have, how many fixed points it has. So in this case, I have the m squared. M is the same as k. K squared is 3, and this thing here is greater than or equal to 2 times 1. And there is here just one little place here where some base locus could come up, and you might say, oh well, it's pretty unlikely, it's not going to come up. But in fact it does. As soon as you allow the surfaces to have some little singularity, some little possibility of existing in a singular setup, immediately they will do it. And so, everything that can possibly go wrong does go wrong in these arguments. Anyway, there's also Horikawa analysis in many other interesting cases, and I'm going to come to this later. But PG equals 3, k squared equals 4 is particularly interesting and still difficult. Okay.
What's the branch locus of this map of the branch covering of the double covering?
There's somewhere in here there's an elliptic curve, so it gets mapped to. I think the double covering has degree 8, if I'm not mistaken, and has not 8, has degree 10, and has a branch locus which has got a straight line contained in it. That's the image of this. And then together with one of these points of type 3, 3, infinitely near triple points. You can deduce it from these equations. There's an elliptic curve hiding in here.
I'm sorry. What about moduli? Moduli space is connected or not?
Yes.
This is the generation of the other.
Yeah. Okay. So if I write lambda times z plus this here, right? When lambda is 0, I see that surface, which is with the base locus. When lambda is non-zero, then this is the linear system x1, x2, x3. When lambda is, if this says that z is a function of the other variables.
Sorry. Okay.
No. I mean, this case is really perfect in that respect. It is showing there is a degeneration that happens, but in this case, the degeneration is not affecting the non-singularity, or this is just a kind of hyperelliptic locus in the middle of the moduli space.
So this is the general case. The triple color is the general case.
This is the general case. This is the special case, and these have a non-singular degeneration to the degenerate guys have a non-singular degeneration to the non-singular smoothing to the non-degenerate case. I'll give this in more detail with the rings on the curves and so on, because it's a very, very good example. This was worked out, geometrically this was done by Horikawa, probably around 1975. And then it was worked out by a Romanian guy called Valentin Iliev around 1985. With a little bit of help from me. Okay. So let's start again in 20 minutes.